All right, if you're an aviation maintenance technician student, you know Chapter 8, corrosion control. It's not just textbook stuff, is it?
Not at all. It's absolutely critical knowledge. We're talking the difference between a simple fix and, well, potentially losing an aircraft structure.
Right. So the mission today, let's really dig into the sources, pull out the essential facts you need, not just for the general exam, but for actually finding and stopping corrosion out there.
Exactly. We need to understand how metal breaks down, why it happens, and what you, as an AMT, actually do about it. It's kind of insidious, this stuff.
Okay, let's start simple. Corrosion, we hear it all the time. But what is it, chemically speaking, for metal?
Basically, it's metal trying to get back to its natural state. Think ores, oxides, salts. It's deterioration through chemical or electrochemical attack.
So it's like the metal is just trying to rust or oxidize naturally.
Pretty much. And it's not just ugly surface stuff. It can change the surface properties, weaken the inside, even loosen up parts next to it. It's a big deal.
What really kicks it off on an aircraft? Because, they operate in all sorts of environments.
The main enemy. Water. Or even just water vapor. Combine that with oxygen, and especially if there's salt around.
The marine environment problem.
Precisely. Flying near the coast or even industrial areas with certain fumes, that just puts the corrosion process into high gear. That's the key trigger.
Okay, so electrochemical attack. That's the big one, right? The sources hammer this point. 4 essential conditions. Get rid of one, and you stop it.
That's the core idea behind prevention, yeah. You need these 4 things to make a little battery, basically. First, a metal that's going to corrode. That's your anode. It gives up electrons.
Okay, metal number 1.
Second, you need a dissimilar conductive material, something more noble, less likely to corrode. That's the cathode.
Got it. Anode and cathode.
Third, you need a path for the current, a conductive liquid, the electrolyte, usually moisture, maybe salty moisture.
The bridge between them.
Exactly. And fourth, you need electrical contact between the anode and cathode. They have to be connected somehow to complete the circuit.
So that could be rivets, bolts, even just wet corrosion products.
Right. Metal-to-metal contact or even that conductive crud can bridge the gap. Once that circuit's complete, the anode starts, well, dissolving, corroding.
Okay, that brings up the galvanic series chart. We see things like magnesium and aluminum way up high active, and gold, silver down low noble. If we know pairing different metals is bad, why do we see so much aluminum skin with, say, stainless steel fasteners? That seems like asking for trouble based on that chart.
It is asking for trouble if you don't manage it. The chart shows the risk. Big difference in potential means faster corrosion. We use aluminum for weight, right? But when we join it to something noble like steel,
High risk.
very high risk. So mitigation is everything. We have to insulate them, break that electrical contact, usually with primers and coatings. We'll get into the specifics later.
Okay, so we manage the known risk. Makes sense. Quickly, though, what about direct chemical attack? That's different, isn't it?
Totally different mechanism. It's pure chemical reaction, no electrical cell needed. It happens right where the chemical touches the metal.
Like spilled battery acid.
Exactly. Spilled acid, maybe some flux left over from soldering, or even strong cleaning solutions that got trapped and weren't rinsed off properly. It's an immediate, localized burn, chemically speaking.
So electrochemical is the slow creep, direct chemical is the fast burn.
You got it. Both need fast action, but how you clean them up is different.
All right, let's talk identification. You're out on the line. What are the first visual clues? What should you be looking for?
Colors are key. For aluminum and magnesium, the really active ones, look for pitting, maybe some etching, and almost always this gray or white powdery deposit.
Okay, white or gray powder.
Steel, that's easy. Reddish-brown rust. Everyone knows rust.
Right.
And if you're dealing with copper or brass parts, look for a greenish film. That's the telltale sign there.
So you see the powder or the rust. Now, what are the forms of corrosion that really worry us structurally? Let's start with pitting.
Pitting is nasty because it looks small but goes deep. You see that white or gray powder on aluminum or magnesium, you clean it off, and bam, tiny little holes.
Just pinpricks.
Sometimes. But those pinpricks can go surprisingly deep, weakening the metal way more than you'd think just looking at the surface. It eats through the thickness quickly.
Okay, then there's exfoliation. That sounds bad.
It is bad. It's basically an advanced stage of intergranular corrosion, attacking along the metal's grain boundaries. The corrosion products build up inside the metal and literally push the surface layers apart.
So it looks like it's flaking or swelling.
Exactly. Lifting up, peeling almost. You see it a lot on extruded parts, wing spars, stringers. Requires NDI like ultrasonic or eddy current to really assess the depth.
And the really weird looking one, filiform corrosion,
Hmm.
the worms under the paint.
Yeah, the worm tracks. It happens specifically under paint, often polyurethane, and only in a specific humidity range, like 78 to 90% relative humidity. Plus, the surface needs to be a bit acidic.
What's the key thing for an AMT to remember about those tracks?
On steel, the tracks never cross each other, but on aluminum, they do cross and overlap. That usually means the attack is deeper and more structurally significant on aluminum, so crisscrossing tracks. Pay close attention.
Okay, one more type I want to hit. Fretting corrosion.
Mm-mm.
Because this one's a bit different, right? Not really driven by an electrolyte initially.
Correct. It's mechanical action plus oxidation. You have two surfaces that are supposed to be tight together, but there's tiny movement, vibration.
Like a rivet.
The classic smoking rivet. Yeah.
Yeah.
That tiny movement rubs off the protective oxide layer, exposes bare metal, which then oxidizes, creating debris. The debris is often abrasive, making it worse. That black or reddish dust around the rivet head, that's fretting. Moisture makes it worse, but the movement starts it.
Okay, so all these types of corrosion, how much you have to worry about them depends a lot on where the aircraft lives and flies, doesn't it?
Absolutely. Geography dictates the maintenance schedule. The regs classify zones: mild, moderate, and severe.
How different are the schedules?
Big difference. Mild zone. You might be cleaning, inspecting, and preserving every 90 days. Moderate zone. That drops to every 45 days.
And severe. Coastal bases, heavy industrial areas.
Every 15 days. That's how fast corrosion can get started in those environments. Cleaning, detailed inspection, and reapplying protective compounds every 2 weeks or so.
Wow. 15 days versus 90. That really highlights the environmental impact and the workload on the maintenance crew. So environment's a factor. But some spots on any aircraft are just magnets for corrosion, right? Where should an AMT always look extra carefully?
Definitely. 3 areas are always top of the list. First, wheel wells and landing gear. Think about it: mud, water, salt spray, gravel, everything gets thrown up in there.
Constant abuse.
Exactly. So frequent, thorough cleaning and inspection are critical, especially around fittings, tubing, and any magnesium parts like some wheels. They corrode fast.
Okay, number 2.
Battery compartments, always a problem area. You've got corrosive fumes, potential spills, sulfuric acid or potassium hydroxide depending on the battery type.
Right, nasty stuff.
And it doesn't take much to start eating away at the surrounding structure. So regular cleaning, neutralizing any spills immediately, that's just standard procedure.
And the third big one, piano hinges.
Ah, yes. Piano hinges, especially on external skin panels. They're perfect traps for dirt, salt, moisture. Plus, you almost always have dissimilar metals, a steel pin in an aluminum hinge body.
Prime spot for galvanic corrosion.
Textbook case.
Yep.
So when you inspect them, you don't just look, you need to lubricate them properly, then work the hinge back and forth several times. Make sure that lube gets in there and pushes any trapped water or gunk out.
Okay, so dealing with those dissimilar metals, like the hinge, if we can't always avoid using them and we can't keep things perfectly dry, insulation is the answer, right? Breaking that electrical circuit. How's that done properly?
Insulation is mandatory. The sources are clear. For most dissimilar metal joints, anything not involving magnesium, you need at least 2 coats of a good primer. Zinc chromate used to be common. Now epoxy primers are often preferred. They act as a barrier.
2 coats. Got it. But what if one of those metals is magnesium? It's super active.
Then the protection level goes up. Magnesium needs more help. It's minimum 2 coats of primer, plus you have to add a layer of physical separation. Usually that's a specific type of pressure-sensitive vinyl tape, about 0.00003 inches thick, applied smoothly over the primer.
Okay, primer plus tape for magnesium. Seems thorough. Any exceptions, like near hot engines?
Good point. There is an exception. If that joint is going to see sustained temperatures over 250 degrees Fahrenheit, that vinyl tape won't hold up. It'll degrade.
So then what?
Then you omit the tape and rely solely on extra coats of primer for insulation. More layers to build up that barrier thickness.
All right, let's shift to actually fixing it. You found corrosion. You need to remove it. What's the absolute standard when you're working on critical, highly stressed parts?
The key thing is, once you remove the visible corrosion, you can't leave any pits behind on critical structure, even tiny ones. They act as stress risers.
Stress risers, meaning they concentrate stress and can lead to cracks.
Exactly. Stress corrosion cracking or fatigue failure under load. So all pitting must be blended out smoothly.
And that blending isn't just random sanding. There's that specific rule, the 20-to-1 ratio.
That's the one. It's mandatory. The depression left after removing the corrosion needs to be blended into the surrounding metal very gradually. The length of the blended area has to be at least 20 times the depth of the material removed.
20 times. That ensures a really smooth transition, minimizes the stress concentration.
Precisely. It maintains the structural integrity as much as possible.
Okay, let's quickly cover removal for different metals. Steel first. Rust.
Yeah, rust just encourages more rust, so you got to get rid of it. Usually mechanically abrasive papers, maybe non-woven abrasive pads like Scotch-Brite. But there's a huge caution here.
What's that?
For high-strength steel parts, like landing gear components, you generally cannot use chemical rust removers without specific engineering approval.
Why not? Seems faster.
Risk of hydrogen embrittlement. Those chemicals can introduce hydrogen into the steel, making it incredibly brittle. It could fail suddenly under load. Mechanical removal is safer for those parts.
Okay. Critical safety point there. Now, magnesium, the really reactive one.
Yep. Corrosion looks like white, powdery mounds, sometimes almost like little whiskers. Because it's so active, the biggest restriction is your tools.
Tools.
You must use non-metallic tools for cleaning. Stiff, non-metal brushes, like hog bristle or non-woven abrasive pads again. Never use steel tools, steel wool, wire brushes, or even aluminum tools or brushes on magnesium.
Why such a strict rule? No metal tools at all.
Because if tiny particles of steel or aluminum get embedded in the magnesium surface, maybe from a wire brush, you've just set up a perfect little galvanic cell, add moisture and you'll get severe corrosion right where you cleaned. Keep those tools completely separate.
Wow. Easy mistake to make if you're not thinking. Okay, finally, aluminum. Especially alclad or anodized surfaces.
Right, those have protective layers. With alclad, the goal is to remove the corrosion without removing too much of the pure aluminum cladding layer, if possible. Once that's gone, the underlying alloy is much more vulnerable.
And anodized surfaces.
Anodizing is an oxide film. You can't really restore it fully in the field. You clean the corrosion carefully, then maybe use a chemical treatment like a chromic acid inhibitor to provide some temporary protection. But mostly, you want to avoid damaging the good anodized film right next to the corroded spot.
And underlying all of this removal and treatment?
Yeah.
Safety. These chemicals aren't friendly.
Absolutely not. Mandatory reading, the safety data sheet, the SDS for every chemical and solvent you use. Know the hazards.
Like MEK, methyl ethyl ketone. Still see that around sometimes.
Yeah, MEK is a strong solvent, but it's got a really low flash point, like 24 degrees Fahrenheit. That's a serious fire hazard, not to mention it's pretty toxic to breathe or get on your skin.
Low flash point solvents are just risky on a hangar floor.
Very. And that's why regulations have pushed towards replacing them with safer alternatives, higher flash points, maybe less toxic. Always check that SDS. Know what you're handling.
So we've gone through the science, how to spot it, how to fix it. It seems incredibly complex, but also kind of simple in principle.
It boils down to vigilance, really. Corrosion control isn't a one-time fix. It's continuous preventative maintenance. Good cleaning, thorough inspections, dealing with problems promptly when they're small.
And keeping those drain holes clear.
Oh, absolutely critical. Letting water pool is just inviting trouble. You're constantly trying to break one of those 4 conditions needed for the electrochemical cell to work. Mostly, you're fighting the electrolyte, keeping things clean and dry.
You know, the key thing that jumped out from the sources was this idea of foreign materials. It's not just salt water. It could be leftover cleaning chemicals or even something as simple as a pencil mark.
Exactly. Graphite from a pencil can actually set up a galvanic cell with aluminum. Seems minor, but it's a controllable factor.
So for the AMT, maybe the best defense isn't super complicated chemistry knowledge, but just diligence, strict adherence to cleaning procedures, and constant careful inspection.
That's a huge part of it. Think about it the next time you're signing off a cleaning task. Are you just wiping off dirt, or are you actually removing the conditions that allow the aircraft's structure to start decaying?
That's a really powerful way to frame it. Are you just cleaning? Or are you preventing structural failure? Something for every technician to think about.
Definitely.
Okay, I think that covers the essential corrosion knowledge every AMT needs. Thanks for breaking it down with us.
My pleasure. Stay vigilant out there.
Absolutely. We'll catch you on the next one.